Bio. This is Mr. B. We're continuing on with Chapter 17. The title of this section is Earth's Early History. And so what this section is going to focus on is actually how the Earth was formed, or what we think might have happened, all the way up until how life was able to kind of colonize the Earth. So we're going to start with the very origins of the Earth. So the formation of the Earth. So hypotheses about Earth's early history are based on a relatively small amount of evidence. And then it says gaps and uncertainties make it likely that scientific ideas about the origin of life will change. So what this means, kind of the most important thing to know, is that no one was around, obviously, when the Earth was first formed. So we do not know exactly how it happened. We can only just make guess on what it says on a relatively, or not guesses, hypothesis, on a relatively small amount of information, on a relatively small amount of evidence. So the most important thing we need to know about the formation of the Earth is that we really don't have a good way to explain it right now. We have some evidence, but there are gaps and uncertainties that make this likely it'll change multiple times throughout the course of our lifetime. However, evidence does show that our Earth was not born in a single event, so it wasn't just like, oh, there's Earth, all of a sudden perfect how it is today. So what they think might have happened is that pieces of cosmic debris, so what cosmic debris means is just things from space, so it could be like meteors, comets, asteroids, things like that, and says that they were probably attracted to one another over the course of 100 million years. So what happened was things started coming together, the pull of gravity just started bringing more things in closer and closer and closer over the course of 100 millions of years. And then while Earth was young, probably a big object struck it, or is struck by one or more objects, and it produced enough heat to melt the entire globe. So what happened was, we think, again, no one was obviously there, all of these things started to come together, then it was after it came together to form a solid, it got struck by a huge object or multiple objects, and the entire globe that we had melted. And so once the Earth melted, its elements rearranged themselves according to density. So density is just how, like, basically how much something weighs is kind of like the simpler way to say it. So what things were heavier. And so the most dense, so the heaviest, formed the planet's core. So after they all melted, all the heaviest elements fell down, and they formed the center, which is the core of the Earth. And so then our moderately dense elements floated to the surface. They cooled, and they formed a solid crust. And so then and then there's the layers below it as well, would be formed, just kind of going up in density as we go. And then our least dense elements, they formed our first atmosphere. So they didn't stay connected to the solid mass, however, they still stayed within the pull of Earth's gravity, and they formed our first atmosphere. So this is just a hypothesis. So again, no one was there to tell us what actually happened, so this is just a guess of what we can think happened based on the limited evidence that we have. And so now, we mentioned there, we formed the first atmosphere, so we're going to look at what substances made up our Earth's early atmosphere. So our earliest atmosphere probably contained things like hydrogen cyanide, carbon dioxide, carbon monoxide, nitrogen, hydrogen sulfide, and water. And there's one big thing missing there that's necessary for us today, and that is obviously oxygen. So there was no oxygen in Earth's early atmosphere, and so therefore probably that's why we didn't have a lot of life at that time. And so scientists infer, so then again, that's just kind of a faint scientific guess there, that about 4 billion years ago, Earth finally cooled down. So again, it got hit, everything melted, so there's a lot of volcanoes, a lot of heat going on at that time. And so after it cooled, solid rocks formed on the surface. And so this was about 4 billion years ago is when it started to cool. And then millions of years later, more volcanoes came around and shook Earth's crust. So once it finally cooled and settled down a little bit, volcanoes started going crazy. And then about 3.8 billion years ago, Earth's surface cooled enough for water to remain a liquid, and oceans covered much of the surface. So we finally have some water. That's kind of our first building block there to actually maybe start some life, because nothing really was going to want to live in hot molten lava. So water, about 3.8 billion years ago, first showed up. So then after water, we needed some organic molecules. So remember, these are just kind of things that are made out of carbon, is basically what organic means, is just made out of carbon. And then, so we needed molecules to help us start building the life forms that we're all made of. So we couldn't just all poof out of nowhere. We needed something to kind of build on. And so we need to look at the question that could organic molecules have evolved under conditions on early Earth? So could have these things come around and all of the thing with the kind of the crazy atmosphere that was going on Earth? And so in the 1950s, so these are two important guys, Stanley Miller and Harold Urey, Stanley Miller and Harold Urey, they tried to answer the question by simulating Earth's conditions, by simulating conditions on the early Earth in a laboratory setting. So they wanted to simulate what Earth used to look like in an early setting. So with all that high temperatures, the hydrogen cyanide, all of those things, they wanted to simulate that. And so what they did is they came up with this apparatus right here. So up here to start, they had a spark which simulated lightning storms which were going on during this time, a chamber that kind of will help where condensation would occur because we knew there was water at that time, so there would have to be evaporation and condensation, so that was going on, and then forming the water droplets, and then there was water vapor obviously because there was water, and then there's the mixture of, and then he added in the mixture of gases that simulated the atmosphere of early Earth. So this he kind of had. This was all contained off, all blocked off, and this is what basically Earth's early atmosphere in a nutshell, if you will. And so what they did was they kind of put this all together and they wanted to see what the results were, just basically having all this stuff mixed together. And so they suggested their experiments. I'll just start over here. So Miller and Urey's experiments suggested how mixtures of organic compounds necessary for life could have arisen from simpler compounds present on primitive Earth. So within this closed-off system, they had, if you can see here, this most important part, the resulting liquid contained amino acids and other organic compounds. So as a result of all these things mixing together, they showed that amino acids and other organic compounds could in fact form. And although their simulations of Earth were not accurate, so they weren't completely and 100% correct because, again, we don't know exactly what was going on at that time, and this was, again, in the 50s. Current experiments with the knowledge they had have yielded similar results. So it does show that our building blocks, our amino acids, which remember are building blocks of proteins. Proteins are the building blocks of our cells. So it shows that the amino acids could have formed under these circumstances. And so now we have answered how the building blocks of life came around. So now we need to look at how actual life came around. So our evidence suggests that 200 to 300 million years after Earth had liquid water, cells similar to modern bacteria were common. So there were cells floating around in this water that were similar to our modern bacteria. However, they were a little bit different and they had a different name. And we'll get to those now. And their name is going to sound confusing, but if we just break it down, it makes sense. So in certain conditions, our large organic molecules form tiny bubbles called protenoid microspheres. So these are going to be on your tests, but however, protenoid just means made of protein, obviously. Microspheres, micro just means small. A sphere is just like a circular shape. So these are just small, circular shaped proteins. That's all they are. And these are not cells, however, but they had a selectively permeable membrane, which this is a big vocabulary word from first semester, meaning they can choose which passes through, and they could store and release energy. So they had characteristics of cells, but they were not exactly cells. And hypotheses suggest that structures similar to microspheres might have acquired more characteristics of living cells. So these microspheres might have been our precursors to cells. So that is it for this first section. We'll finish it up tomorrow. Let me know if you have any questions.